So quantitative analysis, when we have solutions, is very similar to gravimetric stoichiometry. Basically, we'll be able to predict the yield when we react to solutions. We can also use it to identify how much of a substance is present. So we're going to do a couple of examples based on quantitative analysis with solutions. So example number 1. Determine the minimum volume of sodium sulfate that is required to react completely with all the barium ions in a barium chloride solution. So we are mixing two quantities of two different solutions together, and we're going to make sodium chloride solution and barium sulfate precipitate. So far, all we've done here is a double displacement reaction and balanced it, put in our subscripts. Set up these questions exactly like you did with gravimetric stoichiometry. Put what you know below each substance. So we know we have 0.42 moles per liter sodium sulfate. So that's our concentration, our molar concentration. We want to find the volume of this. We have concentration of barium chloride of 0.1 mole per liter, and we have 500 milliliters of it. Change your volume to liters. So divide by 1,000 and get liters. So again, this is just like gravimetric stoichiometry. We're given information about one substance and have to calculate a missing piece of information about a different substance. And we're going to do it exactly the same way using mole ratios. I'm sure you're all very excited about that. So, we know concentration is equal to moles divided by volume. So if we have concentration and we have volume, we can find moles. So moles is equal to concentration times volume. I'm going to use formulas first, and then I'll show you using dimensional analysis. So moles is equal to the concentration times the volume. So for barium chloride, we have 0.1 mole per liter times a half a liter. So this is 0.05 moles of barium chloride. We need to find volume of sodium sulfate. So we have to convert barium chloride to sodium sulfate. So multiply it by the mole ratio. There's 1 sodium sulfate required for every 1 barium chloride. So we have 0.05 moles of sodium sulfate. So now we have moles of sodium sulfate, concentration, we can find volume. So going back to this equation, rearranging it, we would have moles divided by concentration to give us our volume. So we're going to take 0.05 moles of sodium sulfate divided by 0.42 moles per liter. So this is 0.119 liters. If you multiply that by 1,000, it's 119 milliliters, 2 significant digits, 120 milliliters. So therefore, in this reaction, we would need to react 120 milliliters of sodium sulfate with 500 mils of barium chloride. So if we're going to do this using dimensional analysis, we are looking for, in the end, the units that we're looking for are liters of sodium sulfate. So at this moment in time, there's only one number up there that has liters of sodium sulfate in it, and that is this concentration. So liters is on the bottom, so we're going to invert that ratio. 1 liter of sodium sulfate contains 0.42 moles of sodium sulfate. So we just inverted the concentration. We've got to get rid of moles of sodium sulfate. There's no number up there that represents it. It's the mole ratio that you have to use instead. There's 1 mole of sodium sulfate for every 1 mole barium chloride. So moles of sodium sulfate are gone. We're left with moles of barium chloride, which we have in our concentration. There's 0.1 mole of barium chloride for every 1 liter of barium chloride. So moles of barium chloride are gone, which leaves liters. So we need to get rid of liters of barium chloride, and we happen to have half a liter of barium chloride. So now the only units that are left, liters of sodium sulfate. So in your calculator, you've got we've got 1, check out this arrow, 1 times 1 times 0.1 times 0.5 divided by 0.42. for 2, 1, and 1. Cool. Didn't know I had that arrow. And you should get 119 liters, which is 2 significant digits, 120 milliliters. So if you're going to use dimensional analysis, you're going to start with inverting the concentration of what we're looking for, mole ratio, concentration of what we have times the liters of what we have. Okay, the next example. Predict the mass of precipitate expected when we have sodium carbonate, we have 0.8 moles per liter, we have 1.5 liters, and we make sodium nitrate and aluminum carbonate. That is not a balanced chemical equation, so we're going to have to balance that. We have 1 mole per liter aluminum nitrate, and there's 850 milliliters. Divide that by 1,000, and we've got 0.85 liters. So we need to multiply this by 3, this by 6, and this by 2. That's going to make for lots of mole ratios. Okay. Predict the mass of precipitates expected. Well, which one of our products is a precipitate? We've got sodium nitrate. All nitrates are soluble, so it's not that. So it's our aluminum carbonate. So we want to know the mass produced of this, so we need to find the molar mass of that as well. And that is 233.99 grams per mole. So this is a question just like we did before. We figure out which reactant is limiting, and then that produces the least amount of product, which is our maximum mass of product. So we can use formulas, or we can use dimensional analysis. So I'll show dimensional analysis first this time, and then I'll do formulas. So we want to find mass of aluminum carbonate. So what we have to do is find what ratio up there has grams of aluminum carbonate in it, and that is the molar mass. So we're going to start, so we're going to do this first for sodium carbonate. We start with a mass of aluminum carbonate. So molar mass of aluminum carbonate. I think I should have picked compounds without polyatomic ions for this one. Okay, mole ratios. The mole ratio of aluminum carbonate to sodium carbonate. We look back at our balanced chemical equation. Here we go. Oh, I can make them flash. All right. So we've got 1 and 3. Got rid of aluminum carbonate. Now we're down to sodium carbonate. And we've got moles. So now I want to get rid of moles of sodium carbonate, and you can see over here that we have a quantity with moles sodium carbonate. So there's 0.8 moles of sodium carbonate for every 1 liter, and we have 1.5 liters. Moles of carbonate, sodium carbonate go, liters go. We're only left with grams of aluminum carbonate, which is what we want. So in our calculator, we will multiply 233.99 times 1 times 0.8 times 1.5 divided by 1 divided by 3 divided by 1. And that will give us the maximum mass we can produce of aluminum carbonate from all of our sodium carbonate getting used up. So this is equal to 93.596 grams of aluminum carbonate. Okay, so now we're going to repeat using aluminum nitrate. Let's just move this up a bit. Okay, so again, we are trying to figure out the mass of aluminum carbonate. So we're going to start same place, 233.99 grams of aluminum carbonate for every 1 mole of aluminum carbonate. There's 1 mole of aluminum carbonate for every 2 moles of aluminum nitrate. So these will cancel out. We have up here 1 mole of aluminum nitrate per liter, and we have 850 milliliters of it. So 1 mole of aluminum nitrate for every 1 liter, and then multiply this by 0.85 liters. So moles of aluminum nitrate cancel, liters of aluminum nitrate cancel. So you're left with, in your calculator, you will take 233.99 times 1 times 1 times 0.85 divided by 1, divided by 2, divided by 1. And you will end up 99.446 grams. So, compare these two numbers. Got almost 100 grams if all the aluminum nitrate gets used up, and you have almost 94 grams if all the sodium carbonate gets used up. So, it appears that sodium carbonate gets used up first and is the limiting reagent, and the maximum mass of product, maximum amount of product that you can make is 93.6 grams of aluminum carbonate. So this is just one of the ways to show how to use doing formulas. We've got C, we've got V, you can find moles. It's equal to concentration times the volume. So the moles of sodium carbonate is equal to 0.8 times 1.5 liters. For aluminum nitrate, it's 1 mole per liter times 0.85. Find those values. Once you have those values, convert them to moles of product. So 1 mole of aluminum carbonate for every 3 moles of sodium carbonate. And do the same thing for the aluminum nitrate. So that's 0.425 moles of product. So compare these two numbers. This one is smaller, therefore sodium carbonate is the limiting reagent. And now we have to figure out the mass of product you can make. So you're going to multiply that number by the molar mass. So round that off. 93.6 grams of aluminum carbonate is formed.